Hello and welcome to Math Zone African Motives. Today, we're going to dive into a powerful technique for finding roots of equations. By the end of this video, you will be able to understand the core idea behind Newton's method and use its formula to approximate better roots of functions. So what exactly is a root? In algebra, the roots of an equation are the values of the variable for which the function's value is 0. In other words, they are the solutions to f of x equals 0. These are also known as the zeros of the function. Let's write that down. A root is a value for which f of x equals 0. Graphically, the roots are the x-intercepts, where the graph crosses the x-axis. We can easily find roots for linear functions, like a x plus b equals 0, or for quadratic functions using the quadratic formula. But what about more complex functions, like cubics or others for which there's no simple formula? In many such cases, there's no exact formula we can just plug numbers into. For example, consider the equation e to the power of negative x minus x equals 0. How would we find its root? When we can't find exact roots, we can find approximate roots. That is, roots that are very close to the actual value. In this video, we'll learn a systematic method for finding increasingly accurate approximations. Let's first see how we can get a rough estimate of a root. A common technique is the sign change method, which we can visualize with a table or a graph. Here's the question. We need to show that a root for the equation e to the power of negative x minus x equals 0 lies between 0 and 1, and then show it's between 0.4 and 0.6. First, let's define our function, f of x, as e to the negative x minus x. Now we will evaluate the function at x equals 0 and x equals 1 to check for a sign change. At x equals 0, we have e to the power of negative 0, which is 1 minus 0, which gives us 1. This is a positive value. At x equals 1, we have e to the power of negative 1, which is about 0.368, minus 1, which gives us approximately 0.632. This is a negative value. Because the sign of the function changed from positive at x equals 0 to negative at x equals 1, there must be a root somewhere in that interval. Think of it graphically. A continuous line must cross the x-axis to go from a positive y value to a negative y value. Let's make this explicit. A sign change implies there is a root between the two x values. Now let's narrow it down. We'll complete the table for values between 0.4 and 0.6. We need to calculate f of x for x equals 0.2, 0.4, 0.6, and 0.8. Evaluating the function at these points, we get the following results. F of 0.2 is approximately 0.618. F of 0.4 is 0.270. F of 0.6 is 0.051. And f of 0.8 is 0.351. Let's highlight the key point in the table. Notice that the function's value changes from positive to negative between x equals 0.4 and x equals 0.6. This sign change confirms that the root we are looking for is located within the interval from 0.4 to 0.6. This method works well for finding an approximate range. While the sign change method is useful for a rough estimate, it can be very slow if we need high accuracy, like to 4 decimal places. Here's where we need a better tool. The method we will learn is called Newton's method. It's a powerful and efficient technique for improving the accuracy of our approximated roots. Let's understand the geometry behind it. Imagine we have a curve y equals f of x and it cuts the x-axis at a root, which we'll call r. We can't read this root r accurately from the graph, so we make an initial guess. Let's call it x1. We find the point on the curve directly above x1, which is a with coordinates x1, f of x1. Now, the genius of Newton's method is this. We draw a tangent line to the curve at point A. This tangent line is much simpler than the curve itself. Where does this tangent line cut the x-axis? Let's call that point x2. As you can see, x2 is usually much closer to the actual root r than our original guess x1. This is our better approximation. The whole process is then repeated. We use x2 as our new guess, draw a new tangent, find its x-intercept, which we'll call x3, and that will be an even better approximation. Each step gets us closer to the true root. Now, let's derive the formula that turns this geometry into a calculation. This formula is what we'll use to apply Newton's method. We know that the gradient, or slope, of the tangent line at any point on a curve is given by its derivative. So the gradient at our point A, which is x1, f of x1, is simply f prime of x1. We also know that we have 2 points on this tangent line, ax1 f x1, and the new approximation b equals to 0. Using the slope formula, rise over run, the gradient is f of x1 minus 0, all over x1 minus x2. So we can equate these two expressions for the gradient. We have f prime of x1 equals f of x1 divided by x1 minus x2. Now we just need to rearrange this equation to solve for our new approximation, x2. First, multiply both sides by x1 minus x2. Then expand the bracket on the left. Next, rearrange the terms to isolate x2, and finally factor out the negative sign. This gives us our result. This formula gives us the next, more accurate approximation, x2, in terms of the current approximation, x1, and the function and its derivative evaluated at x1. We can generalize this process to find any approximation in a sequence. This gives us the general formula for Newton's method. The next approximation, xn plus 1, is equal to the current approximation, xn minus the ratio of the function's value to its derivative's value at xn. The beauty of this iterative formula is that you simply repeat the calculation, feeding the result of one step back into the next to get an even more accurate answer. How do we know when to stop? We continue the process until the level of accuracy required is reached. For example, if we need the root correct to 4 decimal places, we stop when the first 4 decimals of xn and xn plus 1 are the same. A quick word of caution. Newton's method can fail if the derivative f prime of x is equal to 0 at any point xn. This is rare, but it means the tangent line at that point is horizontal, so it will never intersect the x-axis to give us the next approximation. Let's apply Newton's method to our previous problem to see how quickly we can find a highly accurate root. This is our first major example. The question asks us to find the root of e to the negative x minus x equals 0, correct to 4 decimal places. We already know the root is between 0.4 and 0.6. Step 1 is to define our function and find its derivative. Our function is f of x equals e to the negative x minus x. The derivative f prime of x is negative e to the negative x minus 1. Step 2 is to choose an initial guess, x1. A good starting point is often the midpoint of the interval we found. So we'll choose x1 to be 0.5. Now we can begin our first iteration. We calculate f of 0.5 and f prime of 0.5. It's crucial to use your calculator's memory function here to keep full precision and avoid rounding errors. For our first iteration, we calculate x2 using the formula. Plugging the values in, we get x2 is approximately 0.5663. This is already a much better approximation. Now we move to the second iteration. We use our new value x2 as the input. Remember, the key is to use the full unrounded value of x2 from the previous step. We calculate f of x2 and f prime of x2. Next, we calculate x3, our third approximation. Again, plugging these values into Newton's formula, we find that x3 is approximately 0.5671. Let's compare this to our previous approximation, x2. Highlighting x2 and x3, we can see that when rounded to 4 decimal places, they are not yet the same. We need to perform one more iteration. Using x3 as our new starting point, we calculate f of x3 and f prime of x3. We find the new function and derivative values. Now for the final calculation, x4. Look closely. When we calculate x4, we get a value that is the same as x3 when rounded to 4 decimal places. The first 4 decimals have stabilized. Since x3 and x4 both round to 0.5671, we can confidently state that the root, correct to 4 decimal places, is 0.5671. By using only 3 iterations, we have arrived at an accurate result that would have taken many, many more steps with the sign change method. This demonstrates the power of Newton's method. Now let's try another example. This time, the function is a cubic, and we are given a graph to help us get started. The question asks us to use Newton's method just once to find better approximations for two different roots of the function f of x equals x cubed minus 2 squared minus 2x plus 3. We'll round our answers to 3 decimal places. Let's look at the graph. It clearly shows 3 x-intercepts, meaning there are 3 real roots. We are interested in the 2 on the left and right. As before, our first step is to find the function and its derivative. Our function is f of x equals x cubed minus 2x squared minus 2 plus 3. The derivative, f prime of x, is 3 plus x squared minus 4 plus minus 2. Now, let's solve the first part, finding a better approximation for the root near negative 1.3. We will use negative 1.3 as our initial guess, x1. Next, we evaluate the function and its derivative at this point. Substitute negative 1.3 into both functions. We find that f of negative 1.3 is 0.023 and f prime of negative 1.3 is 8.27. Now we apply Newton's formula once to get our better approximation, x2. Plugging in our values, we calculate x2. The result, rounded to 3 decimal places as required, is negative 1303. This value of negative 1.303 is a better approximation of that root than our initial guess of negative 1.3. Now let's tackle the second part of the question, finding a better approximation for the root near 2.3. We'll follow the exact same procedure, but this time with a different initial guess. Our functions are the same. Our new initial guess, x1, is 2.3. Step 1 is to evaluate the function and its derivative at this new guess. Substituting 2.3 into f of x gives us negative 0.013. Substituting it into f prime of x gives us 4.67. Now for step 2, apply Newton's formula one time to find our better approximation, x2. We plug the calculated values into the formula. The result, rounded to 3 decimal places, is 2.303. So 2.303 is a better approximation for this root than our starting guess of 2.3. This example shows us that we can use the method multiple times for multiple roots, as long as we have a reasonable starting point near each root. The process is the same for each one. It's important to note that for this specific problem, there's a simpler way to find the exact roots, which the lecture notes show. Because the function has an obvious root at x equals 1, we can factor the cubic and then use the quadratic formula to find the other 2 roots. This would give us the exact answers, which are 1.303 and 2.303, matching our Newton's method results perfectly. This is a great point. Always look for simpler, exact methods first. Newton's method is a last resort, but an incredibly powerful one for problems where exact solutions are impossible. Let's conclude with a final example from a past paper. This problem asks us to do a full function analysis of a cubic before using Newton's method. First, we'll find the turning points by setting the first derivative to 0. Then we'll find the point of inflection by setting the second derivative to 0. The first derivative, f prime of x, is 6x squared plus 2x minus 3. Setting it to 0 gives the x-coordinates of the turning points. We use the quadratic formula to solve for x, getting approximately 0.56 and negative 0.89. We then substitute these x values back into the original function to find the corresponding y values. This gives us our 2 turning points. For the point of inflection, we find the second derivative, which is 12x plus 2, and set it to 0. This gives us x equals negative 1/6. Substituting this into the original function gives us the point of inflection. Next, we would draw a table of values and sketch the graph. Let's fast forward to the main part of our lesson. The question asks us to use Newton's method to find a better approximation for the root that is close to negative 1.8. We start with our function and its derivative. Our initial guess, x1, is negative 1.8. Now we evaluate f and f prime at x1. f of negative 1.8 is negative 0.024. f prime of negative 1.8 is 12.84. We can see that the root lies between negative 1.8 and a slightly smaller number, as f is negative. Finally, we apply the Newton's method formula. We find our new approximation, x2. The result, when rounded to 3 decimal places, is negative 1.798. If we wanted more accuracy, we would repeat this step with x2 as our new guess. but the question only asked for a single approximation rounded to 3 decimals. Let's recap what we've learned today. We explored the powerful mathematical tool known as Newton's method. We began by seeing that while simple equations have direct formulas for their roots, many complex equations do not. This created the need for a reliable approximation method. The core idea is to start with an initial guess and use the tangent line at that point to get a better, closer approximation. This geometric insight is key. We derived the general formula, which allows us to iteratively improve our approximation. Each application of this formula brings us closer to the true root. We saw how to apply this method with several examples, learning to calculate derivatives, evaluate functions, and use our calculators efficiently. A crucial takeaway is the importance of using your calculator's memory function to maintain accuracy. So, whether you're dealing with transcendental functions, high-degree polynomials, or any other equation without an obvious solution, Newton's method is a fantastic tool to have in your mathematical arsenal. Thank you for joining us on Math Zone African Motives. If you found this video helpful, please subscribe for more tutorials. See you next time.